Okay, we are on calculating with chemical change, stoichiometry, and in the warm-up it says write a balanced equation for the reaction between chromium metal and hydrochloric acid to form chromium 3 chloride and an unreactive gas. So chromium metal would be Cr, hydrochloric acid is HCl, it's a binary acid. You're forming chromium 3 chloride, we cross the charges. And this is a single replacement reaction, so the chromium and the hydrogen switch places. So that means you're going to form hydrogen gas. Now, this isn't balanced. I need to put a six in front of HCl because chlorine and hydrogen, the lowest common multiple of 2 and 3 is 6. So that would require a 2 in front of CrCl3, a 3 in front of H2, and then I need a 2 in front of Cr. And it says if 2 moles of chromium metal completely reacted, so here are my 2 moles of chromium metal, in an excess amount of hydrochloric acid, meaning I have more than enough hydrochloric acid, how many moles of hydrogen gas would be formed? Well, it would be 3 moles because I would use that coefficient. Number 3, how many moles of hydrogen gas would form if 4 moles of chromium metal were completely reacted? So that means that this would be doubled, which means I would end up having 6 moles of hydrogen gas formed. Now, a balanced chemical reaction tells you the amount of chemicals that are involved. And we can use the coefficients to convert from moles of reactants to moles of products or vice versa. And we may also use it to convert to moles of one reactant to moles of another reactant or moles of one product to moles of another product. And the key is to use a mole ratio, which is determined by the coefficient. So a mole ratio is the ratio of the coefficients of the substances that we are looking at. So I can convert moles of substance A to moles of substance B using the coefficients. So let's take a look at the next page here. If a student puts 7.5 moles of chromium metal in excess hydrochloric acid, how many moles of hydrogen gas are formed? So we're just going to use the balanced equation that is already written, and you will notice that I wrote what we were given underneath chromium. I'm going to circle its coefficient, and then I'm going to look for how many moles of hydrogen I can produce. I'm going to circle its coefficient. So I'm going to need to do a mole ratio using the coefficients in front of chromium and hydrogen, because technically these moles, this coefficient stands for 2 moles of chromium, reacts with 6 moles of hydrochloric acid to produce 2 moles of CrCl3 and 3 moles of H2. So that means I've got 2 moles of chromium for every 3 moles of H2, and I can write this as a fraction. So I'm going to take the number in the unit that I'm given, and you have to indicate what that substance is. So I have 7.50 moles of chromium. The coefficient on chromium is a 2, so it follows you onto the diagonal. So this right here is the coefficient on chromium. Then I'm going to hydrogen, so it's on top. So I have 3, which is the coefficient on hydrogen in the balanced equation. So 7.50 times 3 divided by 2 will give you 11.3. Now we're going to use that here in the practice problems. How many moles of ammonia are going to be formed by combining 15.7 moles of nitrogen gas with a large excess of hydrogen gas? So this is nitrogen combining with hydrogen to form ammonia. I'm going to need a 3 in front of H2 and a 2 in front of NH3. So here's my balanced equation. I've got 15.75 moles of nitrogen, so I recommend you put that near nitrogen in the balanced equation so you know where you're starting. And we're looking for moles of ammonia. And we have the hydrogen excess, which means I have more than enough of it to react. We're going to write down 15.7 moles of nitrogen. Moles of nitrogen needs to follow you onto the diagonal here. And then you're going to have moles of ammonia on top. The coefficient in front of N2 is going to go here. The coefficient in front of NH3 will go here. 15.75 times 2 is going to give you 31.50 moles of ammonia. Okay, I started with 4 sig figs. I'm going to end with 4 sig figs. For number 2, it says how many moles of water must be decomposed to form 9.45 times 10 to the negative 5th moles of oxygen. So water will decompose to hydrogen and oxygen gas, which are diatomic. And then here is my balanced equation. I've got 9.45 times 10 to the negative 5th moles of oxygen here. We want to know moles of water. So I'm going to be using the coefficients in front of my oxygen and my hydrogen to complete the problem. So moles of oxygen has to follow you onto the diagonal here. These have to match. I'm going to moles of water. The 1 coefficient in front of O2 will go here. The 2 coefficient in front of H2O will go here. In your calculator, this is going to be 9.45 second E negative 5 times 2, enter. And you're going to get 1.89 times 10 to the negative 4 moles of water. Number 3, how many moles of calcium metal are required to replace 1.86 moles of silver from a solution of silver nitrate? So that means calcium is combining with silver nitrate in a single replacement reaction. This is a metal replacement, so calcium will replace silver. You'll kick out silver and you'll get calcium nitrate. Here's your balanced equation. And if we have to look for moles of calcium, and we've got our 1.86 moles of silver, we're going to be using these coefficients here. So it's 1.86 moles of silver. Moles of silver follows you onto the diagonal. And then we're going to moles of calcium. So the 2 in front of silver goes here. The 1 in front of calcium goes here. 1.86 times 1 divided by 2, you're going to get 0.930 moles of calcium. Okay, now let's talk about converting. We're going to put a step on the front of this and the step on the back. You know that you can convert grams to moles and moles to grams. So that means if I'm given grams of substance A, I can convert to grams of substance B, but I have to go to moles of A first, and then, so this would be grams of substance A to moles of substance A, then moles of A to moles of B, moles of B to grams of B. Okay, so this is going to be a longer problem. So if we take a look here at this sample calculation, we're going to use the balanced equation that they've already given us. We have 3.50 grams of silver nitrate, and we want to know how many grams of the precipitate, which would be the silver chloride, are formed. You have to convert your grams of silver nitrate to moles of silver nitrate, and we do that by dividing by the molar mass of silver nitrate. Then you'll convert to your moles of silver chloride, and this will be using the coefficients. And then you'll convert to grams of silver chloride by multiplying by the molar mass. So you can see this is a three-step problem. So here is your first step, grams to moles. The number that goes here is your molar mass. And you'll always have the number 1 on the top next to moles, which is what they've done here. Then you have your silver nitrate coefficient, which is 2, going here. You're going to silver chloride, which has a coefficient of 2, so that will go here. And then you're going to convert from moles of silver chloride to grams. The 1 goes on the bottom next to moles. The number that goes here is the molar mass of silver chloride, which they calculated here. So this is the setup. You're going to get 2.95 grams of silver chloride. Now, if you take a look at the next page, we have some practice problems. Number 1 says, the following reaction is exceptional in that a single reactant species is oxidized and reduced at the same time. What mass of oxygen gas, so I'm going to put a question mark grams next to the oxygen, is going to be formed by the decomposition of 45.65 grams of KClO3. Okay, now I am converting my grams, and I'm just going to give you a little setup here so you understand. I'm going to be given grams of some substance. In this case, it was grams of KClO3. Then here, the number that goes here is going to be your molar mass of KClO3. And 1 mole of KClO3 will be on top. Then moles of KClO3 follows you onto this diagonal. And what goes here is the coefficient that is on KClO3. And then on top, we're going to O2. So the number that would go here is the coefficient on O2. Moles of O2 follows you onto the diagonal. You will always have a 1 next to it. And then the molar mass of O2 will go here. So this is the setup that you follow anytime it's a gram of substance A to gram of substance B problem. This is A, all right in here where your KClO3 is, and B is where your O2 is, okay? So if you look at your periodic table to get the molar masses, I've already calculated them for you. This is 122.55. The coefficient on KClO3 is a 2. The coefficient on O2 is a 3. So this goes here. This goes here. The molar mass of O2 is 32. You'll put this in your calculator. You're going to get 17.9 grams of O2. I stuck with 3 sig figs. I'm not really sure why I did that, but I did. Technically, you probably should have had 4 sig figs in your answer. Okay, let's go on to number 2. For number 2, it says the unbalanced equation shows one possible set of products for the reaction of aluminum and nitric acid. So let me balance this for you. It's 2, 6, 2, 3. Determine the mass of nitric acid. So we want to know HNO3 in grams. And we are forming 170 kilograms of hydrogen gas. Okay, 170 kilograms converted to grams is a one-step metric conversion. So this is going to be 1.7 times 10 to the 5th grams. Let me double check that. I don't do math in my head much anymore. Sometimes I do, sometimes I don't. Okay, we're good. All right, now, I'm going to take what was given. So I was given 1.7 times 10 to the 5th grams of H2. So this is what I was given. This was my given mass. Okay? Now, on the diagonal, you're going to put grams of H2, and on top you put 1 mole of H2. And the number that goes here, this is the molar mass of H2 from the periodic table, which is 2.02. Then, moles of H2 has to follow you onto this diagonal here, and the number that goes here is the coefficient of H2, which is 3. So a 3 goes here. I'm going to moles of HNO3. The number that goes here is the coefficient on HNO3 from the balanced equation, and that is a 6. Moles of HNO3 follows you onto this diagonal. It will always be 1. The molar mass of HNO3 will go here. And the molar mass of HNO3, I calculated it, it's 63.02. You should end up with 1.1 times 10 to the 7th grams of HNO3. Okay? Number 3 is a variation, and you should watch that, scan that QR code with your phone, watch that, and write down how to do number 3. Let's go to number 4. Number 4 says, write a balanced chemical equation for the reaction between sodium, metal, and water. Okay, so sodium reacts with water. It's going to replace the hydrogen in the hydrogen hydroxide. You'll kick out hydrogen gas. You'll form sodium hydroxide. And this is your balanced equation. How many moles of hydrogen gas will form if 2 moles of sodium reacted with excess water? Okay, so I've got a mole to mole conversion. So this is a one-step problem. So I'm given moles, right? I've got 2 moles of sodium. So this is what I'm given here. Moles of sodium will follow you onto the diagonal. What goes here is the coefficient that's on sodium, which is a 2. And then what goes here is the coefficient on H2, which is a 1. And this is going to give you 1 mole of H2. What volume would this gas occupy at STP conditions? Well, standard temperature and pressure, this is a gas. 22.4 liters is occupied by 1 mole of any gas. So if I have a mole of hydrogen gas, it's going to occupy 22.4 liters. Let's go to the next page. Let's look at converting volume to volume. Okay, the volume to volume conversions are special cases, and we're allowed to use a shortcut thanks to Avogadro. Avogadro's hypothesis said that equal volumes of gases contain equal numbers of particles under the same conditions of temperature and pressure. So if that's true, that means equal volumes of gases have the same number of moles under the same conditions. So volumes of gases are going to react in the same proportion as moles of gases. So what you need to make sure of is that when you're looking at a reaction, when all of the states of matter are gases, your coefficients are not only in moles, but they're also in liters. And this is if all of the states of matter are gases. So that means I can do mole ratios as liter ratios if they are all gases, which offers me a really convenient shortcut. Now, Avogadro's hypothesis, again, and I'm just trying to emphasize this, it's only applicable to gases. So if you take a look at the quick check, it says use the balanced equation in the figure above to determine how many moles of carbon dioxide would form from the combustion of 10 liters of propane gas. So we are using this example above. We want to know liters of carbon dioxide gas forming from 10 liters of propane. So since these are all gases, I can use the coefficients as liters. So here, this is a given volume here. Liters of C3H8 follows me onto the diagonal. The number that goes here is the coefficient on C3H8, which is a 1. So I put a 1 here. Then I'm going to liters of CO2. The number that goes here is the coefficient that is on CO2. So this is a 3. So this is going to be 30 liters of CO2. So I can do this liter to liter problem, liters of A to liters of B, because everything is a gas in that equation. Let's go to the next page. Here in the sample problem, they want to know how many liters of ammonia, I'm going to use their balanced equation, are produced with an excess amount of nitrogen, that means I have plenty of it, with 15 liters of hydrogen gas at STP. You'll notice these are all gases. And what I can do is I can do a liter to liter ratio. This 15 liters of H2, this is the given volume. The number that goes here on the diagonal is the coefficient for H2 in liters, and then the coefficient on NH3 will go here on top in liters. So you have your 2 over 3, which would give you 10 liters of NH3. Now, if they want to know the mass of nitrogen gas that's required to produce 45 liters of ammonia at STP. I'm going to erase this and I'm going to rewrite this with my 45 liters above NH3, and they want to know how many grams of N2. Well, that's a different variation of this problem. So what that means is we would come down here, let me rewrite this. And this is what you are given. This is your given volume. Since you have liters of NH3 here, it follows you onto the diagonal, and the number that goes here is the coefficient of NH3, except it will be in liters. So this 2 follows you down here. And then, I shouldn't have drawn that arrow. Let's make it going around. And then here, you're going to have the coefficient on NH3. Or I'm sorry, that's, let's back up a second. Let's do this a different way. If you are at STP, then since you're at STP, you know that 22.4 liters is the volume occupied by any mole of gas. So this is the given, since we're not doing a liter to liter conversion like we were up above, you're given a volume here, and we're at STP, and since I'm going to grams, I would have 22.4 here always, and I would have 1 mole on top always. And this moles of NH3 would come onto the diagonal, and this is where you're going to put your coefficient of NH3, which was a 2. So this would go here. And this is where you would put your coefficient for N2, which is a 1. That would go here. And then if you're going to grams, you will always have 1 mole here. And then the number that goes here with the grams of N2, this is your molar mass of N2. So your molar mass of N2 was around 28. And then your molar mass of NH3, or I'm sorry, I don't need that. I have everything I need, I believe. This is 28.02. You're going to come out around 28 grams of N2. So that is a little more complicated. So let's go here to the practice problems. Let's take a look at number 1. So here we have a reaction where they're all gases. They want to know the volume of oxygen. So I'm going to put a question mark liters above oxygen. That's going to oxidize this much sulfur dioxide. So this is 2.41 times 10 to the 7th liters. So this is a liter to liter conversion, which is a one-step conversion because I can use the coefficients as liters. So I'm given 2.41 times 10 to the 7th liters of SO2. On the diagonal goes liters of SO2. And what goes here is the coefficient of SO2, which is a 2. And then on top, we have liters of O2. So what would go here is the coefficient in front of O2, which is a 1. So this is going to end up being 1.21 times 10 to the 7th liters of O2. Now, for number 2, we have an unbalanced equation. Put a 2 in front of NaOH, a 2 in front of H2O, and a 2 in front of NH3. And they want to know how many liters of ammonia. So I'm going to put a question mark liters above ammonia, measured at STP. Let's make that note. And we've got 40.5 grams of ammonium sulfate. Okay, so I'm converting grams of ammonium sulfate to moles of ammonium sulfate. Then I have to go from moles of ammonium sulfate to moles of ammonia and then liters. So this is going to be grams. So I am given 40.5 grams of NH4 to SO4. So this is my given mass right here, okay? Grams of NH4 to SO4 goes here, and 1 mole will always go on the top. So this number here is the molar mass of my NH4 This is 132.17. Now, this is where I will put the coefficient of my NH4 which is a 1. And this is where I will put my coefficient for NH3, which is a 2. If I'm going to liters and I'm at STP, I will have 1 mole down here, always, and 22.4 liters here, always. This will give me 13.7 liters. Now, for number 3, I'm going to give you the balanced equation. What mass of HCl has to be contained in a solution with excess zinc arsenide to obtain 17.5 liters of arsine gas at STP. Okay, I'm given liters. I can convert to moles using 22.4 liters. And then I'm going to convert moles to moles and then moles to grams. So if you're given a volume, it will go here. On the diagonal, you will always put 22.4 liters. On the top, we'll go 1 mole, always. The number that goes here is the coefficient, which is a 2. And on top, we'll go the coefficient of HCl. And then you will always have 1 mole down here on the diagonal, and then you will have the molar mass here. And the molar mass of HCl is 36.46. You get 85.5 grams of HCl. So this is a liter of A to grams of B problem. So your A was your ASH3, your B was your HCl. Up here, number 2, this is a grams of A to liters of B problem. So your A was the ammonium sulfate, your B was your ammonia. In number 1, this was a liters of A to liters of B problem. A was SO2, B was O2. Okay, now we are on solutions. Now, for solutions, we're going to be using molarity, which is moles per liter, to do some conversions. And they have added that to our wheel model. So let's take a look at the next page. This quick check is a review of molarity that was completed in a previous section. So, for instance, if you have 117 grams of sodium chloride and you're going to a volume of 1.5 liters, what's the concentration? Meaning, what is the molarity? So you have to convert grams to moles by dividing by the molar mass. And once you get moles, divide it by liters to give you molarity. For number 2, they want to know the molarity from question 1 to determine, use the molarity to determine the mass of NaCl in 250 milliliters. So remember that we can use this molarity triangle if we have molarity in liters to get moles. If we cover it up, you would take your 1.3 molarity times your 0.250 liters to give you 0.325 moles of NaCl, and then you would convert moles to grams by multiplying by the molar mass of NaCl, which is 19.0 grams. Now, for number 3, what volume of a solution of the same molarity is going to contain 39 grams of sodium chloride? To solve for volume, you need moles over molarity. So I have to convert my 39 grams of sodium chloride to moles. .667 moles of sodium chloride. Divide that by my molarity, and that will give me 0.51 liters. So that was your little review of molarity. Now, we can use this molarity to convert between moles and liters. Let me show you an example. What mass of nickel wire, so we want to know this in grams, reacts with silver nitrate in 1.25 liters of 0.15 molar solution? Okay, so what you want to do is, we're given liters of silver nitrate. We can use our molarity. Remember that you can set this up differently if you find it easier. We always need to ask ourselves, how can I get to moles? You can get to moles if you multiply molarity times liters, which is what they're doing. They're simply writing it a different way. They're simply writing it this way. Here is your liters. Here is your molarity because it's moles per liter. Okay? This will give you moles. Then what you would do is you would take your coefficient of 2 for your silver nitrate. It would go on this diagonal. We're going to nickel, which would have a coefficient of 1. And then you would convert to grams of nickel by putting the molar mass here, which is what they did down here, which is 58.7, and they got 5.5 grams of nickel. You don't have to set up the molarity and liters this way to cancel out the units. If you want to just multiply them to get moles, that's totally fine. So let's take a look at this practice set. For practice problem number 1, what mass of potassium metal, so I'm going to put a question mark grams under K, is going to produce 250 mils of 0.45 molar potassium hydroxide. So that's 0.25 liters and 0.45 molarity. Always ask yourself, how can I get moles? Well, if I have molarity in liters, then what I can do is multiply to get moles of KOH. So 0.45 times 0.25 is going to give me 0.1125 moles of KOH. And I'm not rounding to the proper number of sig figs. I'm just kind of writing whatever it gives me in the calculator. Then step number 2, we're going to convert our moles of KOH to moles of K using the coefficients. So remember, moles of KOH goes onto the diagonal. I have a 2 coefficient, which goes here. And then I'm going to potassium, 2 moles of K. So that's going to give me the same moles of potassium. And then I've got to convert to grams. So moles to grams of potassium, I'm multiplying by the molar mass, which is 39.10. And that's going to give me 4.4 grams of potassium. You can do that all out in one long step if you would like. this is a special type of problem where you're given molarity in liters and you multiply them to get moles, and then you use your coefficients and then go to mass. So for number 2, what I want you to do is I want you to scan the QR code with your phone and then write down the work, because that is a different type. There are so many variations on the different types of problems that you could get here. Let's look at number 3. How many liters of carbon dioxide gas are going to be formed at STP? You've got phosphoric acid reacting with potassium carbonate. You're going to form carbon dioxide and potassium phosphate and water. So I'm just going to go ahead and give you this balanced chemical equation. So we've got 1.5 liters and 1.75 molarity of phosphoric acid, and we have to know liters of carbon dioxide gas. And they told us that we are at STP, so we can use 22.4 liters per mole if needed. How can I get to moles? Molarity times liters. So step number 1, molarity times liters is moles of H3PO4. Step number 2, we're going to use the coefficients. We're going to go from H3PO4 to CO2. So we will put 2 moles of H3PO4 on the bottom, 3 moles of CO2 on the top. And then what I can do in step number 3 here is, since I am at STP, this right here is my step 3. I can use 22.4 liters per mole to get me to 88 liters of CO2.